The next motivation for using partial derivatives we're going to think about is the application of multivariate Taylor series. So we talked about the Taylor series already based on one variable, and it's an expansion in increasingly high derivatives of the function you want to approximate times increasingly high polynomials of the coordinate to which you're taking the derivatives divided by the factorial of the increasingly high term in the series that you're going to. The multivariate case is similar, but let's first focus on why we might want to use it. Here I've drawn just a little topological map of a function that depends on both x and y. And now you could take a slice and say, let's just set y equal to this value, and then we know that function no longer evaluated at that fixed value of y. That function just depends on x, not explicitly on y. If we hold x fixed, or if we hold y fixed, and so we could certainly do a Taylor series at any point along that line, but it would only allow us to vary back and forth in the x direction. We would only get the variations along that line. Similarly, we could hold x fixed and move up and down as a function of y, and we could write out a Taylor series holding the x fixed going up and down. What the multivariate Taylor series does is, suppose we're using this point as the point that we're expanding on, we are going to write it in such a way so that if we were to hold y fixed, we could go left and right in the x direction, or if we were to hold x fixed, we could go up and down in the y direction, or in fact we could go in any direction diagonal or in any other way around that point, and we would get a Taylor series that would apply equally well in all the directions. So you can imagine that this is a little bit more complicated because we're not only going to need the x derivatives holding y fixed, that is the partial derivative with respect to x, and the y derivatives holding x fixed, that is the partial derivative with respect to y, but some kind of blend so that we can go on diagonals away from there. So I've written out the Taylor series for this two-dimensional function just to show you how it looks. I've actually written out the sum form. So if we're expressing this function, which depends on both x and y, that's the thing that we have the topographic map for. Depends on both x direction and y direction. And we wanted to expand it around this point, we're going to need to know the coordinates for that point. And so it's going to take two different values, a and b. So a is the value of x at this point, and b is the value of y at this point. So we're going to use both of those to express this location that we're going to expand around. Okay, so it's a double sum. First we sum on n, which goes from 0 to infinity, and n is the order. So if n just goes to 0 and we truncated and got rid of the rest, then we wouldn't take any derivatives at all. We'd just be evaluating the function at this point. But if n goes to 1, then we have to have a different variable, which is k, which goes from 0 up to the value of n. So it goes up to 1 if n is equal to 1. And what that allows us to do is it allows us to both express a linear dependence on x, so x minus a. It looks just like our old Taylor series that we're used to. And that would be the case if k was equal to 0 and n was equal to 1, there would just be a dependence on x. But if n was equal to 1 and k was also equal to 1, then there would be no dependence on x, but there would be a dependence on y. And then the downstairs part keeps track of what the divisors will be. These are two different factorials. There's one for k and one for n minus k. All right. So now let's take a look at the derivatives part. And so in those two cases, if we had n equals 1, we would be taking the first derivative. But if k equals 0, the first derivative would be with respect to x only. partial derivative with respect to x, curly curly, or if n was equal to 1 and k was equal to 1, we wouldn't have any derivatives with respect to x, we just have a derivative with respect to y. So it looks like for at least the first order terms, we just copy both the first order term from x and the first order term, forgetting about the dependence on x and just holding and take the derivative with respect to y. That's not so surprising. But let's see what happens at second order where things get a little more interesting. At n equals 2, we could have an x dependence, x squared dependence, we could have a y squared dependence, or we could have an x times y dependence if k is equal to 1 and n is equal to 2. And we could take the derivative with respect to x, second derivative with respect to x, the second derivative with respect to y, or indeed the derivative of the mixed derivative with first derivative with respect to x holding y fixed, and then first derivative with respect to y holding x fixed. And after we've taken all the derivatives, we're still going to plug in for x equals a and y equals b. And so we see if we compare to this formula down here, which is what we do if we just fix y, so make f of x, f only a function of x, and that's this one where we took the dash line through here, we would get the same 0th order term with n was equal to 0 that we get here. We would get the same x-dependent first order term, but we wouldn't have any y-dependent first order term, and we wouldn't have any y derivatives. So we don't have any sense of the deviations with respect to y, and we surely don't get those mixed ones, which are the x times the y part that we get in this formula that makes this allow us to go in all those other directions off of the following just along a variation in x or just along a variation in y, which would be like this with y swapped in for x. These Taylor series get very complicated very fast. You tend not to express them to very high order very often, but we're going to see that being able to do this, at least to the linear part, near a point is really, really powerful in understanding the maps of a function, how it depends, how it varies in space, and indeed, when we put a little bit of dynamical variability, the idea that you might be following a trajectory around on that topological map, it's going to be really, really important, that linear dependence near a point, which will describe the behavior near that point.